What's up, guys? Today we're doing another video on applications of exponents and logarithms, and in this case we're talking about compound interest, one of the most useful things you'll ever get out of math class and one of the most powerful forces of nature for sure. Whether you're talking about debt and how debt can pile up, whether you're talking about investing and the power of compound interest for making money, either way it's a very important subject to understand, especially when you get out of high school. So we're just going to jump into a few examples here. There's two compound interest formulas you need to know. One of them, this is for compound interest where you have a periodic rate of compounding. So maybe interest is compounded monthly, which means there would be 12 times per year you would compound your interest. Maybe it's compounded weekly, which would be 52 times per year. We'll do an activity later where we'll go through and identify all the different compounding periods. But just know that however many times it's compounded per year, that's n, okay, which appears twice in this formula. T is how many years it'll be invested for. R is the rate, the annual rate. This is just one. P is for principal, is the starting amount, and A is how much you have at the end. Okay, all of these are explained on the right. Feel free to pause it and write these down. The other formula is for continuously compounded interest. This is where instead of compounding every month or every week or every day or every hour or every minute or every second, it's compounded continuously. It's compounded infinite number of times in any given time period. It's infinitely compounded essentially. So you really get into a calculus concept here, but it kind of simplifies the formula really. We use this number E, and remember we talked about earlier that E is actually a number, 2.7 something, and that number is used in a lot of places in the real world. It's a number, it's named after Euler, it's Euler's number, and it just has a lot of applications, but it's used in this formula. The P is the same as it was before, R is the rate, again, same rate we had before, and T is how many years for the investment. All right, so let's just look at some examples. The first few, we're going to be using this formula, okay? If you invest $500 in an account that pays 3% monthly for 10 years, how much money will you have? Okay, 3% is the interest rate. That's 3%. It should say compounded monthly. 3% compounded monthly, and you're going to hold it for 10 years. So we're just going to fill these numbers into the formula. The amount you have at the end is $500, the amount you started with, times 1 plus the rate, 3% is 0.03, divided by how many times per year it's compounded, which is 12. We're going to raise that to the power of 12 times 10. And we can really just put all of this in our calculator, and this is the answer. Now, for those of you that want a little bit of explanation of what's going on here, I can kind of briefly break this down. Normally, when we do exponential equations, or if we were going to gain 3% all at once, we're going to gain 3%. Something's growing by 3%. You would do 1 plus 0.03, right? That's what you'd multiply by. The base would be 1.03. That's 3% growth. What's happening here is it's kind of like we're growing 3%, but instead of just doing 1 plus 0.03 and calling it a day, we're going to do that 3% divided by 12. So instead of adding 3%, we're adding 1/12 of 3%, and then we're going to do it 12 times, okay? So it seems like you're getting 3% for the year. So in other words, instead of making 3% interest, you're going to make 1/12 of that. You're going to divide that interest into 12 parts, and then you're going to do it 12 times. Well, as it turns out, that works out in favor of the interest. You're actually going to get more interest effectively that way. And we can do some activities later to kind of explore this, but just understand that that's kind of what's going on here. Then the 10 is just saying how many years we're going to do it. So even though you're expecting to get 3% per year, you're really getting 1/12 of 3% 12 times. And basically, just like when you multiply, that repeated multiplication builds up to where what you actually end up getting is more than 3%. You're essentially building interest on the interest as you go, rather than getting all the interest at once at the end of the year. All right, so another example, an account pays 6.8% compounded weekly. Weekly, how many weeks are there in the year? 52. So that means we're going to have 52 as our N, how many times it's compounded per year. If you invest $1,000, that's the starting amount. How much would you have after 6 years? That's T, okay? You plug all this in the calculator. Be careful about your parentheses and all that kind of stuff. And you get $1,503.41. Then I have another example. An account pays 5% interest compounded continuously, Okay, so now we're using this other formula here. Okay. So if you invest $800, what will it be worth in 15 years? All right, we're just plugging everything in. 800 was the starting amount. E is just E. It stays there like that. 0.05 is the interest rate, and 15 is how many years. You put that in the calculator, and you can see that you would more than double your money in this case. Now, how can you tell the difference? Well, how do you know when to use E and when to use the other one? Very simple. Is it compounded continuously? Do you see the word continuous in here? Yes, then it's E. If it says compounded any other amount, daily, weekly, monthly, quarterly, the most common ones would probably be monthly. You might see weekly. You might see like bi-monthly and some weird things like that. Anything like that, you're going to be using this formula because that's giving you a number of times per year that it's compounded. All right, so a couple other things we can do with this. Here's a couple, or one more example. It's another way of thinking about it, a different type of problem you could be asked, basically. All right, so if you invest $4,000 in an account that pays 6% interest compounded monthly, how many years would it take to have 10,000? So what we're doing here is one of those problems where we're working backwards. They're giving you the ending amount and giving you the starting amount, and they're just saying how long would it take to get there. So we're not looking for the left side of the equation. We know that. We want 10,000 at the end when we started with 4,000. What we don't know is how long, how many years. Think about where's the question mark? What are they asking? How many years? That means T is the unknown, okay? So let's just plug in everything we know, okay? And then you kind of want to work it out a little bit. Now, as soon as you're comfortable with it, you might want to go ahead and work this part out and see what that is. You can put in your calculator 1 plus 0.06 divided by 12. That's actually 1.005. So at some point, I'm going to just, instead of writing this every time, I'm going to start writing that, okay? Well, the very first thing I want to do is I want to divide the 10,000 by 4,000. Just get that over here. Because remember, I want to get the exponent by itself. That's 2.5, okay? And as I said, this is actually 1.005. Okay, well, if this is 1.005, then I can rewrite this as a logarithm. Log with this as the base, okay, and these switch places. Okay, so log base 1.005 of 2.5 equals 12t. All right, well, now I can say, well, 12t equals this. That's the change of base formula. I can't type this in my calculator how it is, but I can type it by using the change of base formula. That way I have a base 10 and a base 10 that I can put in the calculator. Log of this divided by log of this. Now this part I want to put in my calculator and get 183.72. Just entered that in my calculator to see what it is. Okay. Now I just need to divide by 12 on both sides, and my answer is 15.3 years. That's how long it would take to turn $4,000 into $10,000 at 6% interest compounded monthly. You could also do these reverse questions where they say how long would it take using the other formula that involves E, the continuous formula. Either one works the same. That one's probably even easier, which is why I picked this one because I wanted to give the harder example. You can always check your answers by plugging T back into the equation and make sure that when you do 4,000 times all this to the 12 times 15.3 power, so you work all this into the calculator, you should get 10,000 or something very close to it because you probably rounded here.